Hello and welcome back. Today I want to talk about an odd circuit. One that creates a seemingly impossible parameter, impedance, but the negative kind. This is perfectly doable, but just because it is possible to make does not mean that it's easy. So if you're curious about what something like this could be useful for and my troubled attempt at making it, then keep watching. So let's start simple. The classical components. The resistor, inductor, and capacitor have the following frequency-based impedance behaviors. The resistor has a constant impedance and 0 degrees of phase shift. The inductor has an ever-increasing impedance and a plus 90 degrees of phase shift. And finally, the capacitor has an ever-decreasing impedance and minus 90 degrees of phase shift. So far, so good. But if we move to negative impedance components, well, the impedance behavior stays the same, it has the same frequency-based behavior, but the phase is inverted. The negative resistor presents 180 degrees, the negative inductor behaves like a capacitor at minus 90, and the negative capacitor behaves like an inductor at plus 90. Now, while this property may seem strange, it does allow for some very interesting applications. Today, I will mainly focus on radio frequency circuits, so I want to highlight what a negative impedance circuit could be useful for when working with antennas. Now, most antennas have a similar behavior, so let's use a dipole as an example. The simple equivalent electrical model is that of a signal source in series with some RLC components. This has an impedance curve similar to a capacitor. Impedance drops till the self-resonance point, and then it increases. With no matching, we would use this antenna at, well, the resonance point. Everywhere else, its impedance is very high, so signal pickup is greatly reduced. Now, without modifying the antenna, you can add some extra reactance and shift the usable point. Adding some extra inductance, we can move it lower, or with some extra capacitance, move it higher. So even if the antenna is too short or too long, it can still be made usable, but the important observation is that the point of minimum impedance, where we just see its resistance, is still just a point. You can resonate away the reactance only at a single frequency, using regular positive impedance components. Now, with negative impedance components, we are getting a new behavior. You can completely cancel out the capacitance using a negative capacitor, or the inductance using a negative inductor. In essence, producing a flat response circuit, something that could be efficiently matched over a very wide bandwidth. Now, this is not just a mathematical oddity. It has been proven to work quite a long time ago. So, one of the oldest papers that I found on this subject is this declassified Army paper, where active antenna matching circuits are being analyzed. And well, without going through the details, and skipping right to the end, where all the results are, what the researchers are highlighting is that you can indeed get a far more flat impedance response by using negative impedance converting circuits. So either by compensating just one parameter, like capacitance in this case, or capacitance and resistance, or well, capacitance and inductance. So by doing this, you are able to provide matching over multiple decades of frequency. This other paper, this time a NASA paper on extremely low frequency active antennas, and here one of the mentioned points refers to the antenna's interaction with the electromagnetic wave. So with a regular antenna, the wave induces a current into the antenna, which in turn creates its own field around it that interacts with the incoming wave, but the magnitude of the induced current is limited by the antenna impedance and just how well it's matched. But by using negative impedance circuits, you can force a larger than normal current through the antenna by compensating its internal resistance, thus making the current larger. So the interaction with the incoming wave is stronger. So in other words, at least for electrically small antennas, you can make them behave as if they were physically larger. But while this paper does not give a clear improvement factor, the last paper to highlight today is one that specifically looks at the signal-to-noise ratio enhancement when using negative impedance circuits. And well, here they are reporting a 7 decibel improvement in signal-to-noise ratio. So I will be leaving links to all of these papers in the description, of course. Today's video is sponsored by PCBWay. To assess the negative impedance converter, I ordered a set of boards to see how it works. We will later test these out and see how they behave. Now, if you're unsure, you can quickly get an idea of what a set of boards would cost. So you can easily quote now, insert some basic specifications of the board, like dimensions, quantity, number of layers, and any other specific property, and quickly get an estimation of what it would cost. You get multiple build options, either the standard build time or, well, faster ones, and based on the country you're from, you will also get quite a lot of shipping options. So you can try out PCBs as well as other products from PCBWay using the link in the description. So just to summarize, you can make an active circuit which has the potential to make an antenna impedance stable over a wide frequency range, and the antenna even works better than it should, since it can pick up more signal even if it's electrically small. So why isn't negative impedance antenna matching widely used? Why is it such a niche subject? Let's now look at how such a circuit could be implemented using op-amps. So the basic op-amp implementation of a negative impedance converter centers around, well, an op-amp and 3 impedances. The observed impedance being derived from this formula. So while all impedances are positive, there is a minus in front, so you can get a negative impedance value based on how the components are chosen. Now, you may have noticed that I didn't completely draw the op-amp. The inputs have not been marked. This was intentional, because both versions will work. The difference is that one is called a current inverting negative impedance converter, while the other is a voltage inverting negative impedance converter. But the impedance calculation formula does stay the same. So we can quickly confirm that this works by performing a small signal AC analysis. So I took as reference a 100 microhenry inductor, and we will be comparing this to the negative versions built with both the voltage and current inverting configurations. So if we run the circuit and we plot out the voltage in our first circuit, so this is proportional to the inductor's impedance, an ever-rising quantity with a plus 90 degrees of phase shift. Now this can be compared to the impedance as seen by the two AC signal sources. So for this I used the .NET statements, and if we plot these out, so we add the two input impedances, well, we can see that there are some small deviations, but regardless, we are observing the same ever-rising impedance, but this time the phase shift is negative. It's around minus 90 degrees. So the behavior presented by these circuits is inverted to that of the regular inductor. So this is what negative inductance behaves like. So the circuit works just right. The theory and the simulation results line up quite nicely. Or do they? Well, the AC simulation seems to be just right, but that is not the only type of simulation that you can perform. Just to be on the safe side, I took the same circuits, removed the injection source, and ran a transient simulation, just to see the time domain behavior. So the expectation here is that since there's no injected signal, the negative impedance converter has nothing to react to, so the input should be at 0. And well, if we check, with the first circuit, the signal just shoots up to the positive rail with a bit of oscillation and then stays there. And if we check the second circuit, well, it just oscillates uncontrollably. So as it stands, both these circuits are unusable at the moment. While negative impedance converters have multiple drawbacks, they consume a lot of power, require a lot of components, they add noise, all of these issues pale in comparison to the fundamental reason these are so rare. Getting a negative impedance converter based circuit to not oscillate is, let's just say, a challenge. These circuits rely on positive feedback, and unless you perfectly control this, you end up with a massive headache. So the simplest and most elegant explanation for what the stability condition of an op-amp-based negative impedance converter I found goes something like this. The negative feedback value needs to be larger than the positive feedback value. Regardless of the voltage or current inverting version of the circuit, if we treat it as an op-amp connected to 4 impedances, to keep this thing stable, the positive feedback, the impedances on the left side, need to provide a smaller signal than the negative feedback, the impedances on the right side. This condition needs to be met not just at the frequency of interest, but at every frequency point from DC up to where the op-amp passes its unity bandwidth point. And that is why this is not a simple problem to solve. When I first set out to build a negative impedance converter, my goal was to connect it to an antenna and show the many benefits, just like the literature predicted. But after building a couple of oscillators, my goal shifted to just make a negative impedance converter. Simply be able to show negative impedance. It shouldn't be that difficult, right? So, after multiple iterations, this is the circuit that I came up with. It's built around the AD8055 op-amp using a single 10-volt supply, so a half supply point is used as reference, and the incoming signal is AC coupled into the input, but also there's an AC coupling capacitor in the feedback loop. And the whole point of this circuit is to provide negative inductance. So the 50 microhenry real inductor should be seen as 50 microhenries of negative inductance. Now, for a more realistic simulation, I also added in the inductor's series resistance, as well as some amount of parallel capacitance. So, if we simulate the circuit in a transient simulation, and we look at the input, well, it's stable. It's not oscillating. And the voltage that we see, 5 volts, is half of our supply voltage. So far, so good. We can also move to an AC type of simulation and see that the impedance of a 50 microhenry inductor is more or less the same as the impedance presented by our circuit, but it's phase shifted. So at least in the 100 kHz up to a few megahertz range, we are getting both the right impedance value as well as the inverted phase. So this circuit might actually work. So of course, this is the circuit that I built, and it was time to test it out. I connected it to a power supply and an ADP to measure the impedance. This thing injects AC signal from a 50 ohm signal source and measures the impedance using 2 oscilloscope probes, observing the injected signal over a known resistance, 100 ohms in my case. So this is the setup that I will be using for today's measurements. So just before running the impedance measurement, let's first check what the oscilloscope probes are showing us. Yet another successful oscillator. So the best way of checking the stability condition that I could find was to simply take an AC source and rebuild both feedback paths, and just observe the positive and the negative feedback value. So with the equivalent of our original circuit, if we plot this out, well, the positive feedback, the blue line, is always smaller than the negative green line. So the circuit is stable. However, if we modify this a bit and include our measurement equipment, so the 150 ohms connected to our input terminal, and we re-simulate, well, this time the negative feedback presents a dip which crosses the positive feedback line. So the circuit oscillates. Now we can correct this by first of all adding a resistor in parallel with our inductor, and secondly playing around with the positive feedback loop. So with these two different components, we reduce the amount of negative feedback so that it stays above the positive one. So this way we should be in the stable region even with our 150 ohms of measurement equipment. And when we remeasure, another successful oscillator. So another thing that I missed when building the model was that the oscilloscope probes have capacitance. If we add, say, 22 picofarads where the probes would be connected, and we check the two lines, Well, the negative feedback dips a bit more, just enough to cross the limit. So this time I had enough and decided to play with the positive feedback one more time and add a 56 picofarad capacitor on the low side. So by doing this, we should move the positive feedback line out of the way and leave a bit of margin for any tolerances that occurred when we created the initial model. So this time, does it work? Well, when I turn it on, nothing happens. Is it broken? Let's check the impedance. And well, there you have it. A miracle has occurred. Negative impedance. In the 30 kHz to about 1 MHz region, we are getting the increasing impedance characteristic of an inductor, and the phase shift is minus 90 degrees. It's finally stable, and it finally works. So this is what negative impedance looks like. Wasn't that hard now, was it? So, while it is possible to make a negative impedance converter, it's not as easy as the basic circuit makes it seem. Most analyses skip the stability issue altogether. So the reason this circuit is so rare is that keeping it stable while accounting for internal as well as load component tolerances is not always that easy to achieve. And while you can of course make a functional circuit, it's very easy to push it over the edge into oscillation. And that risk is not always worth taking. But it sure is an interesting circuit to try. So with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be updated with my latest releases, also consider subscribing. See you next time. Bye bye.